Global Positioning System, GPS. If you're traveling through a train or waiting for it at a station, flying in an aeroplane, driving a car, involved in a rescue operation, a road construction project, navigating the great oceans, or just walking in a lonely street all by yourself with your smartphone, you most definitely will be needing GPS, if not already using it. Now, GPS is a technology that determines the position of an object anywhere on the planet Earth. To be more specific, it tracks an electronic receiver that is fitted into all of these objects. Yes, into all of these, including your smartphone. So essentially, it tracks that receiver, provides an accurate information about its position, the longitude, the latitude, and the altitude, a point location in all three axes of the three-dimensional world we live in, X, Y, and Z. How? How does it do it? For a better understanding, let us first consider a two-dimensional world scenario where we only have two axes, X and Y, length and breadth, no height, no Z axis. A perfect flat world. Let's try to locate our receiver in that flat world, learn how does it do it, and apply our understanding to the real 3D world then. By the way, this black video screen you are looking at is a perfect example of flat 2D world, where it only deals with length and breadth, no height. Let me take a 2D world map and let's locate our electronic receiver in there. Obviously, I need help. For my help, I have a number of stations. Station A, Station B, Station C, and so on, at different locations of this flat world. One of these stations, say Station A, somehow mysteriously, yes, mysteriously, we'll come to this mystery part later. But let's say somehow mysteriously, Station A tells me that the receiver is at a distance of 3,000 kilometers from it. Well, this yellow line represents 3,000 kilometers. Well, if that's true, then the receiver could be anywhere on this circle, which has a radius of 3,000 kilometers centered at Station A. Let's go to Station B. Station B tells me the receiver is at 2,000 kilometers from it. Well, if that's true, then I got another circle. But now this time my receiver could only be at these two common points, the intersecting points of these two circles, because it has to exist on both the circles of Station A and Station B. So my receiver is either at Romania in Europe or at Congo Forest in the middle of Africa. Now you can see with only one more station and a known distance from that station, I can bring down my search from 2 points to a single point. With the help of Station C, I get one more circle. I can pinpoint my location, which is, in this case, I know for sure that my receiver is at the Congo Forest in Africa. So all you need is 3 stations, 3 distances from those stations, which will give you 3 intersecting circles at a single point. But the problem now is we don't live in a two-dimensional world. We live in long buildings at different floors. We fly in aeroplanes. We climb mountains where height matters. So let's add that height axis, the axis that we left off, the height axis Z, and think about the real three-dimensional world. In a 3D world, each of these stations are no more on the ground, but each of these stations, each one of them, is a satellite. Yes, a satellite. Let me draw these satellites. Every one of them is a satellite that are revolving around the planet in space. And as we all know, a circle in 2 dimension is a sphere in 3 dimension. So to track the receiver, instead of 3 intersecting circles, you need 4 intersecting spheres to pinpoint the receiver in the real 3D world. This process is called trilateration. It's just a name, don't worry about it. Now I know I need 4 satellites, 4 distances from those satellites, which will give me 4 intersecting spheres, and bam, I have my location of the receiver. Well, one last thing, the mystery part. This mysteriously finds, remember? So, the mystery is, how does each of these station or each of these satellite finds the distance of the receiver from its position? That's the last piece of the puzzle, and the answer to that puzzle is radio signals. Let me first draw a planet Earth, and a sample satellite here. Let us first think about a radio tower. We all have seen it. The way the radio tower transmits signals is in all directions simultaneously at a time. If you can see those signals, if you can see them, you would see a sphere around the tip of the radio tower. Exactly like that, the satellite have a tip, and the radio signals continuously transmitted from that tip in all directions, like a sphere around it, like represented in this diagram, like in all directions, a sphere around it. The question is, what does it transmit? It transmits a time signal. Yes, a signal containing some kind of time information through radio waves. Well, the time information that it transmits is signal departure time. Signal departure time. Let's say it is T0. That is the time at which each signal left the satellite. So each signal contains the time at which it left the satellite. The moment that you switch on your GPS receiver in your smartphone or in any GPS tracker device, it picks up that radio signal and also notes down the receiving time. Let's say that is TR. So the total time taken for the signal to travel from the satellite to your GPS receiver will be TR minus T0. Using this formula, distance equal to speed into time, and the time being the time that we have just calculated, the travel time. The travel time is TR minus T0. Because the signal has traveled through radio waves, and the radio waves travel at a speed of light, which is 3 into 10 to the power 8 meters per second. We know the speed too. Substitute that speed in that formula. You know the speed, you know the travel time. So you calculate the distance. A simple multiplication, and you have your distance from the satellite to your receiver. That would be the same distance from station A, this distance, in case of a 2D scenario. So the mystery is solved with a very simple formula. Distance equal to speed times time. GPS technology does the same calculation for 3 other satellites and find 3 more distances. So total you have 4 satellites, 4 distances, and then it applies trilateration, the new word that we have just learned, trilateration, in the 3D world, using these 4 intersecting spheres with these 4 distances that we have just calculated as the radius of these spheres, and with those 4 spheres you get a common intersection point and tracks the receiver's location. Now let's look at some things on general knowledge. To provide global coverage, that is, to track your receiver at any location on the planet, you need 24 satellites revolving around the planet, out of which at least 4 are always visible to any receiver at any location. Let's look at an animation which shows the number of visible satellites to a particular point on Earth as it revolves and as the satellites orbit around it. You can see the number of satellites which are in red, which are visible, is always more than 4. By the way, all these satellites orbit at a distance of 20,000 kilometers above the surface of the Earth. Different countries have deployed their own set of satellites into space for tracking their receivers. The first country who invented this technology is the United States. It started as a military project. They call it Navstar GPS, which gives global coverage. The second was Russia. They call it GLONASS, GLONASS, which also gives global coverage. Let me draw the global coverage with brackets. The third is China. They call it BIDO, which is a regional coverage system. That is, it can only track receivers in this region, around the Chinese subcontinent. Fourth is India. They call it NAVIC, NAVIC, which is also a regional coverage system in this region, right around the Indian subcontinent. These are the currently operational systems for GPS, and some are in development process. One of them is European Union, which is developing a global coverage system expected by 2020. The next is China is also expanding its BIDO, which is a regional one right now, into a global coverage system, which is also expected by 2020. So now that you've learned all these things, let's do a final scroll down from the top of our video lecture. The final scroll down. Let's go up, up, now down. Now you know how GPS works. Before I sign off, one last interesting fact. One of the most fascinating ideas in the entire human history is the relativity of time, put forward by Albert Einstein in 1915, which says time is experienced different under different gravities. If you've seen the movie Interstellar, they have all this time dilation. It's a great movie, I highly recommend it. This amazing idea was only in theory when Albert Einstein proposed it. The world has to wait for almost 60 years to come up with a technology that could test this idea. The GPS technology that you have just learned is that idea, which proves the genius of Albert Einstein and shows the practical application of relativity of time. Fascinating, isn't it? Now, if you want to learn more about this, click on the links below. Now, that's it for the introduction lecture on global positioning system. My name is Gautam, signing off. Namaskar.